Okay, so we're going to talk about descriptive statistics and this topic. And once again, I have to give credit where credit is due. So these are the references that were used to put together this module or these slides. Okay, recall these two terminologies that we just covered in the last, in my previous presentation. We just covered these two topics. So as you recall, when I say population, I mean the entire population that I am studying. So when I say I'm studying the Indonesian people's behavior, I mean literally the entire Indonesian population. But I cannot study every single person, Indonesian person, so I must take a smaller sample to study. And parameters, if you recall, a parameter is to a population what a statistic is to a sample. That means when I measure the height of people in my sample, I obtain a statistic. But when I measure the mean height of, when I say the mean height of all Indonesians, I'm talking about a parameter. So this is practically what we are trying to do. We're trying to study the population, but obviously that is literally impossible. So we take a sample from the population and then we study this sample. So we study whatever it is, the measurement that we need to study. Like, is it the height? Is it the GPA and so forth? And we get the results from the sample, which we use to infer something or to generalize it to make it applicable to the entire population. This is just a repetition of what we already talked about previously. So in order for us to make a reliable inference about the population from the sample, we cannot just take any sample we want. We must do it responsibly using the approved or the standard sampling methods that we already talked about previously. I'm going to skip over this. We already went into that. So when I showed you that cycle, I said that we are talking about a population, we take a sample. We study the sample, we take measurements. Then we use that measurement to infer something about the population. So in order to do that, we need to do what is called statistical inference or inferential statistics. But before we can do any of that, we need to systematically describe the data that we have on the sample level. So in order for us to do any inferences or deducing anything about the entire population, we need to make sure that the statistics we have on the sample level are reliable, they can be presented well. Anyone that would like to understand or see our data is able to. So we need to be able to describe our data and summarize our data set before we can do any inference. This is what is called descriptive statistics. This is the first topic of this course, how we are going to describe and summarize our data set. So I'm going to divide this topic into two main parts: how we can describe our data sets and how we can summarize our data. The first one is describing a data set. When I talk about data sets, I want to be able to present it such that it is understandable for anyone that looks into my data. Why? Because we need to ensure reliability as well as repeatability. So when I say, how would you like your steak? You could say that you would like it well done or rare, I don't know. But when I ask you, how would you like your data? The best way to do it is to give your data clearly and concisely. So I'm going to look into that definition in more depth. It says, in the books, in most theories, it always says you need to present your data clearly and concisely so that whoever looks at your data immediately knows what you're talking about. immediately understands what you're trying to do, what you're trying to measure, what you're trying to present. What does clear mean? I looked it up. It just means that you need to make sure that what you're intending is clear, what your meaning is clear. Concise is not verbose. Use the fewest words possible to convey your idea or your intention or your data. So I could sit here and talk to you about the heights of students in the international class 2020. I could start explaining, okay, so I know I've met before. I met Alexander once. He was really tall, maybe around 170 centimeters. Then I also met Harold, and he was slightly shorter than Alexander, around 170. Can you imagine how much time would be needed for me to explain to you verbally in that detail about every single measurement I took about this 2020 international class? That would be way ineffective. So in statistics, one way is tables and graphs. Those are the most commonly used. You probably have already seen them. You probably have already made them, maybe using Excel, maybe using any other fancy visualization software that even I'm not aware of, but you probably have done this before. And tables and graphs are particularly useful to convey your data quickly, clearly, and concisely. Plus, humans are very visual people. So even in academic papers, it is often suggested to present your data using graphs or using charts instead of putting it in text or instead of presenting a table of values. So in the future, when you take the scientific writing class, that will also probably be conveyed to you that tables and graphs are better than writing down your numbers. Okay, so we're going to focus on two different types of data right now. First, we're going to present a stem and leaf plot, and then we're going to talk about frequency distribution. So we already saw what distribution meant, right? In the previous presentation, I already showed you what it meant by a distribution. Sorry, excuse me for a second. Okay, so first I'm going to talk about the stem and leaf plot. What does it mean? It's a stem and a leaf. You probably already know what, you have an idea of what that means. What's a stem and what's a leaf? So it's a very efficient way to organize small to moderate sized data sets. So you divide your data value into two parts, the stem and the leaf. For example, it's a 2-digit number. We can use the first digit as a stem and the second digit as the leaf. So here, this data point here corresponds to the value 43.7. This one corresponds to 49.0. This one corresponds to 29.3, 29.8, and so forth. Quite straightforward, right? It's the easiest way if you need to, if it's necessary for you to give the exact values of every measurement. Because a lot of the time, if you summarize it in a graph, it's not immediately visible, the exact values of every single measurement. But if you need to, the easiest way is to use a stem and leaf plot. You do not have to divide it like this. It doesn't have to be like you don't have to divide it into the first digit and the second digit. You could, like if your number was in the hundreds, you could use the first two digits as the stem and then the last digit as the leaf, or maybe the first digit as the stem and the two last digits as the leaf. You can make it however you like. But when you're talking about a lot of data, like here we only have, how many do we have? 1, 2, 3, 4, 5, and so forth. If you have a lot of data, or if you have multiple occurrences for the same number, like for example, here we assume that the 33.1 only comes up once. But what if your measurement of 33.1 comes up 11 times? Your measurement of 35.3 comes up 21 times, and so forth. You could alternatively display this as a frequency distribution. How many times this score comes up? In order to describe that, there are some basic shapes or graphs that can be used. You probably have already seen this before. There's the frequency table, line graph, and so forth. And we'll talk about that in the next slides. However, it is necessary for us to first define if you want to group or ungroup your frequency distribution. So the first one is when you ungroup your frequency distributions. So this is just the definition. It can be used for data that is categorical, that is in specific categories, such as nominal or ordinal level data. And there are a relatively small number of distinct values. Sorry, I apologize. Give me a minute to take a drink. I need to cough again. Sorry. Okay, resuming. Sorry, my apologies. So let's look at an example. Suppose you purchased a bag of Skittles. Do they still have Skittles in Indonesia? I haven't seen them in such a long time. But anyway, I purchased a bag of Skittles and I found that there are 55 candies inside. So when I put them into categories, I counted how many times the purple Skittle comes up, the red Skittle comes up, and so forth. Apparently, in my bag, there were only 2 purples, 18 reds, 7 yellows, and so forth. So this is a frequency table, the simplest data display that you could do. It's like for every value on the left-hand side, how many times does it come up in my sample? Simple as that. In this class, for example, I could also categorize how many girls. What is the frequency? I'm actually interested. Let's look at the list. How many girls are there in this class? Anastasia, right? You're a girl, right? And Indira. Any more obvious girl names here? Is that it? Really? There's really only 3? Oh my God. Okay, 4 with me, right? So there are 4 in this particular class. I know that this sample is very small. So this Zoom class has 29 elements in the sample. And from these 29, I could put female 4 and male 25. I could make a table with only 2 lines. So this is the simplest one, a frequency table. I do think that it's very straightforward, and I hope none of you have an issue with it. So now here is another sample of a frequency table. So in this frequency table, this is the graph that I had already shown previously, briefly. This is the starting yearly salaries of 42 recent graduates. So here we have one person getting a starting salary of $60,000 and so forth. This is obviously not Indonesian data. And this is the frequency table. The same, right? It's exactly the same as the one I showed previously. So for every possible value, in this case, we have 47,000, 48,000, and so forth. How many times does it come up in my sample? So 47,000 comes up 4 times, 48 1 time, and so forth. In this case, I can still show the data nicely and efficiently in a table. Because I only have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 distinct values. Imagine if I had like 1,000 distinct values and millions of frequencies. When you're talking about data these days, maybe you've already heard of the term big data, which means that you have a lot of data. So obviously the frequency table will not be a good option in that case. So other than just making a simple frequency table, there are many types of visualizations of frequencies that you could use. For example, I could translate this frequency table into a line graph. See, it's shown as a line for every single distinct value, how many data points falls into 47,000 and so forth. Or I could make a graph. This one I already showed previously. This is the bar graph of that shows the distribution for every single distinct data point. I could also make a frequency polygon as such. So as you can see, each point here corresponds to the value, and then I just make it into a polygon. Or I could also alternatively display the data a little bit differently. Like, for example, when I say, oh, the students, the fresh grads that have a starting salary of 47,000, there are 4 of them. But what does 4 mean? Is 4 a lot? Is 4 only a small portion? It depends on your context. Is 4 in this particular case, I'm talking about 4 students out of 42. So it's significantly small compared to talking about 4 out of 10. So if I have n values, I can talk about the ratio of the frequencies instead of the raw frequency values themselves. And after I have that value, I can then present it in a relative frequency table and a pie chart. So when I want to display a relative frequency table, I want to know in context, what does 4 mean? 4 is out of, what did it say before? 42, right? Yeah. 4 is out of 42. So I could translate it into a relative frequency table so I could get a better context. I could get a better visualization of how many am I talking about here. So if I already have the portion, it is obvious that this is actually a very small percentage. It's only 0.0952% of the graduates that have a starting salary of 47,000. Alternatively, since humans are very visual people, I could also make it into a pie graph that I bet each and every one of you has seen before and probably have made before. Up until now, we talked about singular values. What do I mean singular values? Here, when I'm computing the frequency, I'm saying that there are 4 people that had a starting salary of 47,000, exactly 47,000. Here, I have 1 person that has a starting salary of 48,000. So that means that actually it's not quite significant, the number of people that said 48,000. Why don't I try to group up values in order to present the data a little bit easier? So this is what we mean by a group frequency distribution. Before I continue, I'm going to take a short pause here in order for you to maybe collect your thoughts or review a little bit what we talked about, and for me to take a sip of water. If there are any questions, please bring them up in the chat box. No, not yet. Nobody needs extra time to gather their thoughts? Okay, I'm going to continue now. And by the way, I've also already closed the attendance. So I will be saving the chat log up until now to take the attendance of today. Okay, so now we're going to continue to the grouped frequency distribution. So previously we had singular values for every single frequency. So I actually counted how many times somebody answered 47,000, how many times somebody answered 48,000. And I only had, in this particular case, I only had 11 discrete values. What if I had a lot? And what if the variable is continuous? It would have been a problem if the number was not exactly 47,000. Does that mean that if I wanted to use a ungrouped frequency distribution and my data was continuous, that means I need to check the frequency of every single possible value. Like I would have to record if there was someone with 47.1 of their starting salary, 47.2, 47.3. And then when I already did that, I also have to consider, but what if somebody is 41.18? Where do I put them? So when the variable is continuous in that sense, it's also very difficult to use an ungrouped frequency distribution. So as an alternative, we can also group the data. We can divide the possible values into groupings, or the correct terminology is class interval. And then we can compute the frequency of any value or any measurement that falls into that class interval. For example, here I have the life of 200 incandescent lamps. So as you can see here, there are so many values. I'm not even talking about continuous values yet. I'm still talking about discrete hours. But I have a really wide range of possible values here. As you can see, I have a high value of 1,157. I also have lower values of 658. So it doesn't really make sense for me to actually list every single possible value from 658 until 1,157. It would just be a waste. And every single, it might be that like 658, I have one frequency. 659, there may be zero. There'll be a lot of zeros. It'll be very sparse, my data. So I could group them into groups. There are two ways to do this. We are going to use two main conventions, can we say? Yeah, about how to make these groups. The first one is based on our main textbook, which is the Ross book, Sheldon Ross, and it is the left-hand inclusion convention, which we're going to talk about first. But there's also a very commonly used convention, which doesn't really have a name, proposed by Hinkle in 2003. So let's look at this first. So the first one is the left-hand inclusion convention by Ross. So more or less, when I divide a class interval, so I'm talking about all possible data points that have the value between 500 and 600, 600 and 700, and so forth. And when I say left-hand inclusion, that means that this class interval that says 500 to 600, that means everything greater and equal to 500, but less than 600. 600 is not included because 600 falls into the next class interval. So as you notice, it's written twice. So 500 to 600, 600 to 700. It's not written 500 to 599. But the convention is that the left-hand side is included in the interval, while the right-hand side is not included in the interval. So if I were to translate this frequency table into a more visual graph, I could then make a bar chart like this. A bar graph. Bar chart or bar graph? I guess it's the same. So between 5 and 6, life in unit of 100 hours, I have 2. Between 6 and 7, I have 5, and so forth. So for details in this type of graph, the x-axis represents the possible data value in range, and the frequency obviously is represented by the y-axis. But the y-axis can change if you are representing it using the raw data, which is frequency, the raw frequency, or it's the proportion of data. You could also present it in percentage, like what we already talked about. So you divide it by the total number so that you can give a relative total to the entire sample. And recall, you have other visualization methods, not only the bar chart, but you could also plot the frequency with a polygon, which we already covered before. And you can also plot the frequency cumulatively. This is what it means. So this one is the frequency polygon, which is exactly the same graph as this, but it's only graphed, but it is graphed in a polygon. But I could also count it cumulatively. So from the word cumulative, you probably already have an idea what it means. When the axis represents a possible data value and the y-axis or the ordinate gives the number of data that is less or equal to it. So it will look like this. Note that this is no longer the frequency here is, the frequency here is no longer only for that particular data point, but it means like for in this point, it's 700 or less. This one is 900 or less, and this is 1,100 or less, and so forth. So please note that it will obviously always go up because you are cumulatively adding on to that data. Or you could also describe that. So previously we used the raw frequencies, but now you can also write it in relative frequency. And thus you can see that the y-axis is no longer the raw frequencies, but the relative frequency. This type of shape is also often written in literature as an ogive. I'm not quite sure how to pronounce this word, but so please forgive me. If you know how to pronounce it, please let me know. So you can call this an ogive. I'm not really sure how to pronounce it. So up until now, it was, I showed you the left and inclusion convention, which is by Ross. But there's also another alternative, a significant convention that is used in many literatures, which is the basic group data. So for example, this is a display of the group data for, what is it? Examination scores for psychology students. Let me know, what different things do you see in this table that is not present in the Ross convention? Anyone? You can put it in the chat box. So yes, Alexander already noted that there is something different here. There is a midpoint. So for example, I'm going to point out some different things, not different, some important things from this graph or this table. So the first one, you can notice that there is a class interval of width 5. So here it's 65 to 69. This is 60 to 64. Note that unlike the Ross convention, which left and right, they repeated the value again in the next interval. However, it's not included in the first interval. But here it's different, right? It's 54 and 65. And as Alexander already noted, we have something called the midpoint. Here it says that this is the point midway through the interval. It is not important yet now. However, it will be when you're starting to summarize your data, because when you're computing this particular class interval, for example, the representative, more or less, of this class interval will be valued at its midpoint as its mean. So when you're computing the class interval, you will need to know the midpoint. And this interval means that all scores between 20 and 24 inclusive are included in this class interval. So unlike the Ross convention, where it's only left and inclusive, this one is left and right hand inclusive. So here, if I had a value of 24, it would obviously be in this class interval. If I had 20, it also fall into this class interval. So the assumption here is that we're still talking about discrete values. So I would not have a 24.5 value here. But if we were to have a continuous data, then we would need to change our class interval for us to include the commas behind the number. The disadvantages of this type of grouping is that we no longer know the exact number of students and scores. It only gives us the 6 scores between there are how many scores in a certain interval. So here, when you're talking about the continuous group data, like what I just mentioned, we first of all, the first option is that you could adjust the limits. So you could adjust the limit so that it includes all the commas that you need to be considered in your data. But if that's not possible, you can also use the exact limits, which is, as I mentioned here, when the class interval is 65 to 69, the exact limits are 64.5 and 69.5. So if I were to have a data point at 64.6, obviously it will fall in this class interval. But if it's 64.3, it will fall into the below interval. So students sometimes come back at me with another question. But what if I had a even more specific number? Like, for example, what if my value was 64.457 or something like that? Well, you know how to round up, I presume, and you can round up to whichever limit that you defined. Like, for example, here, the exact limit is 1 digit behind the comma. That means you can round up to 1 digit behind the comma, and then you can classify your data point. Okay. So up until now, we have divided the class intervals seemingly arbitrarily. But how many class intervals are actually needed? If you have too few, then you would have really large intervals and you lose a lot of specific information about the actual data in the class, because then you have just like, for example, if I had used this, if I use this interval and I would say, I use these data, sorry, and I had an interval of 20 to 50 and then 50 to 100. I would lose so much data because I wouldn't know how many are between a more specific interval of numbers. So too few intervals is not a good option. However, if I have too many, then it loses its point. If it's too narrow, then it will also give me a lot of zeros because there may be some empty intervals, and I will lose the data pattern. Plus, it would defeat the purpose of grouping your data if it still ends up with a lot of zeros that we were trying to avoid with the ungrouped data in the first place. So although there is no fixed rule as to how many class intervals you could make, there isn't any rules. There are some guidelines, shall we say, how we can determine the class intervals. So more or less, you can follow this rule that when you have a large data set with a wide range of scores, you can use 10 to 20 intervals. For smaller data sets, 6 to 12 intervals work well. And the width of the class interval is recommended to be an odd number whenever possible, because in the case of the Hinkle group data convention, you will need to define a midpoint. And if your midpoint, if you have an odd number as your interval, it'll be easy to determine your midpoint because it would just simply be the number in the middle, and you don't have to work with decimals in that case. So the group data with the Hinkle convention can also, just like the previous Ross convention, it can be shown, it can be displayed with a bar histogram or a bar chart or a histogram and frequency polygon. You can have a frequency polygon. You could also make a cumulative frequency polygon, just like the previously discussed Ross convention. So after we plot these frequency distributions, usually some shapes will come up. So like this, if I were to plot my frequency of my data, like just like that one, for example, like that one, and I would plot all of my frequencies just like that. After a while, you will notice that there are some special shapes that may come up while you're plotting your data. And there are some special shapes that can give you insight, and it can already tell you a lot about the distribution of samples, which in turn will give you an inkling or a feeling about how the population will be. First of all is the uniform frequency distribution. It's a uniform. Obviously, it's the same. So when you have a shape that is equal for every single possible value, that means you have a uniform frequency distribution. It's just a straight line. It is very rare that this uniform frequency distribution comes up in a natural setting. When you are measuring natural variables such as height or such as GPA and everything, it is very rare that this is the frequency distribution that will come up. Next, we also have the normal Gaussian distribution or the Gaussian frequency distribution. You probably have already seen it before. It's described as a bell distribution. And this is what usually happens when you try to measure something out in the wild or like natural phenomenons. It will usually come up in a natural frequency distribution. You will have the peak in the middle at the median, and it will have you more or less symmetric with one peak, unimodal. But sometimes you don't have the peak in the middle, but you have some outliers. In that case, you have a positively skewed or a negatively skewed to the right, positive skew, and skewed to the left, negative skewed distribution. So in this case, we can deduce that most people fall into this peak area, and there are some outliers on this end, and here is the normal, and there's some outliers on this end. So you can see that's where the tail is, and that one is negatively skewed, and this one is positively skewed. And next, we have a bimodal frequency distribution. So if previously we talked about the normal distribution having only one peak, obviously here it says bimodal, so it has two peaks. If this happens in your data, it likely indicates that when you're talking about the entire population, for example, it means that likely you have two different populations or subpopulations in your study. Like, for example, if I were to study the number of cosmetic purchases of students in Facilcom, for example. So during this pandemic, a lot of people start shopping online, and then a lot of these purchases are cosmetics. Say I were to take that measurement, how many parcels of cosmetics a day do you receive at home? And apparently I come up with 2 peaks. This is likely, this is an assumption, sorry if it's a stereotypical assumption, that when I'm studying the population of Facilcom students, I subconsciously didn't realize that there are actually 2 subpopulations that are doing this online shopping, female and male. And thus, perhaps I will end up with 2 separate peaks in my graph because there are 2 different behaviors of these 2 different subpopulations. So if the skewed frequency distribution is a normal distribution that is slightly skewed, slightly pushed to the right or pushed to the left, now we have a symmetric frequency distribution that doesn't skew to the left or right, but it's slightly pushed together or slightly pulled apart. So that one is a leptokurtic distribution, the one that's narrower in the middle, and the platykurtic distribution is the one that's spread out a little. I usually use a trick to remember which one it is. So the word platykurtic to me looks like platypus, and a platypus is like flat like that with the long beak. So that's how I remember that the platykurtic one is the flat one. Okay, up until here, actually that is halfway through the descriptive statistics material. Does anyone have any questions?